some basic linear algebra operations we get here. Okay? Yeah. All right. After factorization, we know y is a non-zero vector. This 2 by 2 matrix multiplies a non-zero vector equals 0. The conclusion is the determinant must be 0. Yeah. This is a simple but important result in linear algebra. Pretty simple. I will explain why. Yeah. So we can review some basic knowledge in linear algebra. Yeah. But important. Yeah. So here we use this result many times. The first time wrong scan. Second time here. Okay? Characteristic equation. We use this property result. So let's review some more linear algebra properties. All right. First, look at it. A homogeneous linear system with non-trivial solution. So this is a homogeneous linear system, right? With a non-trivial solution. Yeah. So the condition is satisfied. Then the conclusion, okay? Non-trivial solution. Yeah, so this is a homogeneous system with a non-trivial solution, yeah, like that. If and only if determinant of A equals 0. Okay? Yeah. Two-way is fine. If equals 0, then it must have a non-trivial solution. The other direction, if it has a non-trivial solution, then determinant must be 0. Okay? This is linear algebra result. Then I explain. Yeah. Yeah. I explain why. Yeah. Yeah. All right. First, we can see our y non-zero. Yeah. Our y structure like this, you know, E function cannot be 0. Okay? So it must be a non-zero. So then by this theorem, yeah, we can treat it as a theorem. Yeah. By this theorem, we have this determinant of A minus lambda I2 equals 0. By this theorem. Okay? Next, I explain this theorem. Let me explain why. Okay? This nice theorem. Yeah. All right. Let me explain this way. First, let's look at when determinant not equal to 0. What would happen? Yeah, because we can argue in this way. Otherwise, you may argue determinant could be non-zero. If determinant is non-zero, what will happen? Yeah. Let's try to get a contradiction. If determinant is not equal to 0, then A is invertible. Do you know this result? If the determinant of a matrix is not equal to A is invertible. Jenny, do you know it?
What was it again?
If the determinant of a matrix is not equal to 0, then this matrix is invertible. Yeah. Yeah. The other way around also okay. If it's invertible, determinant not 0. Also. So yeah. All right. Yeah. Yeah. So this is one result. So yeah. Yeah. Here I cannot prove because it's too complicated. Yeah. But it is a basic result. Okay. All right. Then, if A is invertible, now here, if you make this assumption, determine non-zero, then our A is invertible. If A is invertible, then an invertible matrix times X equals 0 implies that A equals 0. Can you see that? When an invertible matrix multiply a vector equals 0, because you can multiply its inverse, both sides. You can multiply inverse. Okay? Yeah? Yeah. Yeah. If X equals 0, then we only have trivial solution, because 0 is a trivial solution. That means if the determinant is not equal to 0, you only have trivial solution. You don't have non-trivial solution. That's a contradiction, right? We have a non-trivial solution. how can you assume determinant non-zero? Determinant non-zero will result in only trivial solution, no non-trivial solution. That's a contradiction. That's a contradiction. Okay? Yeah. All right? Yeah. Oh, some of you may feel, yeah, because I saw from your face, some of you have question. You may not get this deduction, right? A times x equals, why you get a equals 0? Yeah, I will explain, okay? Yeah. Here, I give you some basic property of matrix inverse. If A is invertible, then we can use A inverse, right? A inverse is well defined, so we can find the inverse matrix of A. Yeah. Here, let's look at A inverse. If A is invertible, then A inverse exists. Inverse matrix. Yeah. A to the -1 inverse, okay, exists. And its inverse, how do you call its inverse? A times its inverse equals its inverse times A equals the identity matrix. That's the property. You use inverse, multiply the original matrix, you get identity. Okay? But when you multiply those two matrices, you can do two-way multiplication. Okay? Yeah. A times its inverse, or inverse times its A times original equals the identity matrix. Okay. Yeah. So that property. So if we apply this property, now let me apply this property. Okay? Let me apply this property here. Yeah. Yeah. Because I guess some of you may have question understand this step. Some of you may have question understand this step, why it is correct. Okay? Because based on our assumption, A is invertible, right? A is invertible. So A inverse exists. Okay? So now let's take that A inverse. Okay? All right. So we have A times x equals 0. Can we multiply A inverse both sides, left-hand side? The right-hand side, your inverse multiply 0, also 0, right? Yeah. Yeah. Because, so here, if you use inverse, yeah, times 0 vector, this is a 0 vector, also equal to 0. Okay? Yeah. All right. A inverse times A, what's that? It's identity, right? A inverse times A, it is identity. Identity times x, also x, right? Yeah. Identity, we just learned previous slide. Identity times x equals x. So you get x equals 0. Okay? Yeah? Yeah. So after you multiply inverse from the left-hand side, you can get x equals 0. Yeah. Inverse, using inverse. Yeah. 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 But if the determinant equals 0, there is no inverse. A is not invertible. Okay? If the determinant equals 0, you don't have invertible property. A is not invertible, you cannot take inverse. There is no inverse. If there is no inverse, you cannot do operation like multiply a matrix to make the product of those two matrices equals identity. No such matrix. No such matrix. Only when you have an inverse matrix, you can, it's like eliminate A matrix. Using inverse to eliminate original matrix. How good it is. Okay? Yeah. All right. Yeah. So here, review linear algebra. Okay? Yeah. The first time, yeah, but when I have chance, I just keep talking about these basic properties. Try to get you familiar with basic properties of linear algebra. Yeah. All right. But another thing I want to make comments here is, look at here. A times A inverse equals A inverse times A. Is it strange? Do you feel natural or strange? Yeah? Why we write twice? Okay? We know the product of two matrices. Here we write twice. Why we write twice? Okay? Yeah. Because based on your algebra knowledge, when you multiply, let's say two numbers, AB equals BA all the time, right? In algebra. Product of two numbers, which one first, which one second, it doesn't matter, right? In regular algebra, you always have AB equals BA, right? In algebra, 2 times 3 equals 3 times 2. Always like that, right? So we call commutable. Those two numbers commutable, okay? But in linear algebra, you don't have that property. The product of two matrices, in general, not commutable, okay? Yeah, so here, you should be careful. That's why we write twice, okay? So here, yeah, we write twice. They're both true, right? Because in linear algebra, AB not equal to BA in general. Okay? Only in some special case, equal. In the general case, the product up to not equal, linear algebra. Okay? So no commutability property. Matrix multiplication, there is no commutability problem. Nope. Matrix addition, you have commutability problem. Okay? A plus B equals B plus A, always true. But A times B not equal to B times A in general. So that's linear algebra. Okay? So be careful. Yeah. So if you do, commutable, switch the order, yeah, it's dangerous. Yeah. Don't do that. Okay? Yeah. Yeah, but here, because this is an invertible matrix, very special, then when we commute, because they are both equal to A, so they are commute. Yeah, a product of A inverse, commutable. Yeah. All right. Yeah. So now, after this property review, you understand the determinant of A minus lambda I2 must be 0. Now let's calculate. Yeah, we can calculate determinant. What's that determinant? Equals 0, so we should get an equation. Equation about lambda function. Lambda. Yeah, so let's do the calculation. Determinant calculation. Okay. First, I2 equals this matrix. Lambda on the diagonal entries, all lambda on the diagonal entries. Then A minus lambda I equals A matrix, remember A matrix, then subtraction of two matrices, entry-wise subtraction, okay? Entry-wise subtraction. So this entry, negative lambda, we only change the diagonal entries. Diagonal entries, we do subtraction by lambda. Other entries, no change. Other entries of A, no change. Okay. All right. Then we calculate determinant of this matrix. Determinant. Yeah. The cross product, this lambda times parenthesis C over M plus lambda, then minus product of this direction, yeah, diagonal, yeah, minus minus plus, right? 1 times this, you have minus here, but you need to do subtraction. So another minus, minus, you have plus, plus k over m. Yeah. Then, after simplification, you get the characteristic equation that we had before, right? This is the characteristic equation we got from original second order ODE, right? Yeah. So here you can see, after we use 2 different ways to calculate characteristic equations, you can see for the linear system, the way to calculate characteristic equation is this determinant. A minus lambda I. You take determinant, you get a characteristic equation. Okay? Yeah. So you don't need to go back to, you know, some higher order ODE. Yeah. Just calculate it directly. Yeah. All right. So that's this topic. Yeah, characteristic equations. So later, when we have a linear system ODE, yeah, frequently we need to calculate characteristic equation. We use that way, okay, determinant way to do the calculation. Yeah. All right.
Is that the linear transformation eigenvalue?
Yeah, good. Yeah, that really right. So that's the eigenvalues. Yeah, yeah. Later, yeah, we will see eigenvalues, eigenvectors. Yeah, good. Yeah. That's the way we calculate eigenvalues. What are eigenvalues? Eigenvalues, the roots of the characteristic equations. The roots. So we call eigenvalues. Yeah. After we get eigenvalues, we can calculate eigenvectors. Yeah. But why eigenvalue, eigenvectors? Yeah. That part a little harder to understand. So later I will explain, yeah, why we want to calculate eigenvalues, eigenvectors. Yeah. Yeah. A little deeper knowledge you need to have. Yeah. Good. Yeah. So this topic. Next, linearity principle, basis, and a Wronskian for the linear system. Yeah. So here I changed to linearity principle. Yeah. Yeah. Because before we used superposition principle, later I realized many students couldn't get an idea what's the meaning of superposition principle. Yeah, because from the name it's hard to get its meaning, right? If I use the linearity principle, then it's easier, right? We know, all of you know about linearity, okay? Linear property, okay? So you all know that. So now I feel it's better I switch to linearity principle, okay? So you know, so what I'm talking about, yeah. All right. Let's start from this homogeneous linear ODE, yeah, like this, okay? First, about the linearity principle, yeah, also, so superposition, but we prefer use the linearity principle. That is, if y superscript 1, yeah, this notation we treat as superscript, not first derivative, okay? Yeah, do not treat as a first derivative. Superscript, parenthesis. Yeah. Here, do not get confused. Another vector, 2 different vectors, yeah, not derivatives, yeah, are solutions of the homogeneous linear system for, yeah, on some interval. So is any linear combination. Yeah. Y, that is a linear combination, C1, Y sup 1 plus sorry, C2. Yeah, so this number should be C2. Yeah, this is a textbook problem. Yeah, because I did a screenshot. Yeah, this is a textbook typo. Yeah, screenshot. Yeah, C2. Okay, C2. Y sup 2. It's also a solution. That's the linearity principle. Yeah. Okay. Later we just use it. Yeah. Because last time one student asked me, keep asking me why you can use that linear combination to give a general solution. By linearity principle, we can do that. Yeah. That's the meaning of linearity principle. Yeah. Basis, a set of n linearly independent solutions, y sup 1 dot 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 y sup m. Yeah, solution but linearly independent. Then we can call it basis. Yeah. All right. So the general solution after you have a basis of a linear system, ODE, then you can write the general solution y as the linear combination of all the functions in this basis. Yeah, that's the generalization, nothing new. Yeah, yeah. Here we write it out. Yeah, later from now, we will use it. Yeah. We will use it. Okay. Yeah. All right. Then, yeah. So here, all these C arbitrary constants. Yeah. These C coefficients cannot be functions, cannot be C of X function. If C of X function, then won't be original solution of the original equation. If you use function, then you cannot guarantee. Actually, in general, it won't be the solution of the original linear system. Only constant. So that's the meaning from the linearity principle. You can only do linear combination using the constant. Using function, no, it's not linear combination. Okay? When you use non-constant functions, you change the property. Okay? Yeah. You do not preserve the original property. You add new properties. That's not allowed. Okay? Yeah. All right. Fundamental matrix. Yeah. The term fundamental matrix, because we have n vector solutions. Yeah. Each solution is a vector. Okay? Is an n-dimensional vector. So we have n vector solutions. So if we put those n vector solutions together in a matrix, n by n matrix, so we get this Y matrix, capital Y, we call a fundamental matrix. Fundamental matrix. Yeah, because this concept is useful. Yeah. So the reason we introduce this concept, yeah, it will be useful later. Yeah. All right. Now, we can, after we introduce this concept, we can represent a general solution using fundamental matrix to do the representation. What's that? Little y vector equals capital Y matrix times C constant vector. The constant vector, the C, from the constant coefficient. Okay? Yeah. 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 So the general solution can be represented in this way. Okay? This compact way. Yeah. All right? Yeah? All right. Sometimes we may need it. Yeah. Yeah. All right. So that's the, yeah, then Wronskian. Yeah. The last item, the Wronskian definition. Wronskian, just determinant of the fundamental matrix. Okay? So here, Wronskian determinant of the fundamental matrix. Yeah. So they are fundamental matrix. Yeah. So here the version you see there, yeah, the version you see there, yeah, right, right, yeah. So here, yeah, let's take a closer look at this Wronskian determinant. In this Wronskian, let's look at the rows and the columns. Rows and columns. All right. Each column corresponds to one solution in the basis. Now, y super 1 vector, y super 1 vector, the first column. All right? Y super 2 vector, the second column. All right? Yeah. So each column, we use one of the vector solution in the basis. In the basis. Yeah. All right. So the whole matrix inside the determinant, that's just the fundamental matrix. Okay? Yeah. That's just the fundamental matrix. Capital Y. Okay? Yeah. And then those superscript, they are not derivatives. Okay? The superscript, just numbers, different solution numbers. Yeah. Yeah. Because sometimes, yeah, remember if you go back to our higher order derivatives in our notation before, parenthesis, superscript, we use for higher order derivatives. Do not get confused. Yeah. So here the notation, it's very easy to get confused. Yeah. Parenthesis, superscript. Yeah. Yeah, but here it's not derivatives. Yeah. Yeah. All right. Next. Existence and uniqueness theorem. Yeah. All right. Yeah. So the first equation, yeah, so we represent in this way. Yeah. Y1 prime, F1 function. So here you can see this is a general expression. Because in this general expression, we do not need to have a linear system. F1, F2, arbitrary functions, not necessarily linear functions. Yeah. Usually they are not linear functions. Yeah. So our first version of existence uniqueness theorem, not for the linear system, linear ODE. Okay? All right. Yeah. Initial value problems, yeah, corresponding to the ODE, we have the initial value problem. Yeah. Then, existence uniqueness theorem. Yeah, let's look at the condition part. Little f and little f function in equation 1 must be, should be, yeah, yeah. Here we do not say must be, yeah, because it's possible. You know, if not continuous, there is a special case. Still true, right? Yeah, but for simplicity, we just only consider they are continuous function, having continuous partial derivatives. Yeah, continuous in some domain R of T y1 that space. Yeah. All right. Yeah. You know. Yeah. Containing the point T0, yeah. So around T0, there is a small interval covering T0. Around K1, small open interval covering K1, and so on. Okay? How do you understand this capital R domain? Okay? We understand in this way. we look at each component. T0, we expect there is an open interval covering T0. Capital K1, we expect to have an open interval covering K1 and so on. Yeah, all those Ks. Yeah. All right. If that condition is true, then equation 1 has a solution on some interval, yeah, T interval, yeah, yeah, open interval covering T, yeah, satisfying 2 initial value problem, satisfying 2 initial value problem, and this solution is unique. Yeah. This solution is unique. So both existence and uniqueness. Yeah. Actually, you can see this is an extension from our second order ODE. Second order, we have this result. Yeah. Here, just the extension. Second order, remember, we also look at continuous and partial derivative, also continuous. Yeah. Second derivative, second order. Yeah. Here, just more general version. Yeah. All right. Then, now, the first version theorem, non-linear, but second, we restrict to linear. Yeah. This time, this version, you can see equation 3, it's a linear ODE system. Linear, okay? All the coefficient, it's a function, but the multiplication in this structure, matrix multiplication structure, okay? All right, then this existence, uniqueness in linear case, yeah. That letter A, JK's coefficient part, and the G component, G part, in 3 be continuous functions, and a T on an open interval, yeah, containing point T equals T0, yeah, initial condition. Then 3 has a solution y of t on this interval satisfying the initial condition 2, and this solution is unique. Yeah, this solution is unique. Yeah. Yeah. Here you can see for the second version linear case, we only need these functions, A functions, G functions, continuous. Yeah. Here, because the partial derivative, it's simple. Yeah. You can also do partial derivative, but partial derivative, you just get A, A part, yeah. Yeah, Y part gone. Yeah, Y part, when you take partial, it's gone. Okay? You get an A part, and a G partial, yeah. Yeah, G partial gone, all gone. Yeah, G partial all gone. Yeah. So you apply the first version existence unique theorem on equation 3, you can immediately get the second version. It's simple. Okay? Yeah. All right. So that's this topic. Yeah. So we just know. Yeah. So we know this result. Yeah. Yeah. All right. Yeah. All right. So let me move to next topic. Yeah. Next topic, modeling engineering applications by linear systems of ODE. Yeah, let's look at some application questions. Yeah. All right. First, mixing problem involving 2 tanks. Yeah. So we did mixing problem with 1 tank. Yeah. 1 tank. Yeah. So here, 2 tanks. Oh, yeah. So it's that arrow. That arrow. How to remove? Yeah. I don't know how to remove. Anyway, all right. Now look at this two-tank system. Okay, yeah. Tank T1, T2 in the figure contain initially 100 gallons of water each. In T1, the water is pure. Yeah. So no, so what substance? Fertilizer. Yeah. Whereas 150 pounds of fertilizer are dissolved in T2. Yeah. All right. Then, by circulating liquid at a rate of 2 gallons per minute and stirring to keep the mixture uniform in those two tanks. Okay? Yeah. Uniform. The amounts of fertilizer Y1 of T in T1 and Y2 of T in T2 change with time T. Yeah. Two functions. Two functions, solution functions. Yeah. All right. How long should we let the liquid circulate so that T1 will contain at least half as much fertilizer as there will be left in T2? Half. Yeah. From 0 to half of that amount in T2 tank. Okay? Yeah. Yeah. So let's find Y1, Y2 solutions first. Yeah. So then we can calculate, the time needed. Yeah. Initial condition in the first tank, initially pure water, so the amount of fertilizer is 0. Yeah. Initially in tank 2, amount of fertilizer 150 pounds. Yeah. All right. So then we can establish equation using the, what's that? The balance law. Yeah. So we apply the balance law on the two tanks. Yeah. Each tank we can isolate. Each tank we can isolate it and apply the balance law to set up one equation. So two tanks, we apply twice, we get two equations in a linear system. Yeah. All right. So let's write the balance law. For the first tank, yeah, Y1 prime, rate of change in first tank, T1, yeah, equals inflow 1 per minute. Inflow. Okay, inflow 1 per minute minus outflow 1 per minute for tank T1. That's the first linear equation by balance law. Similarly, second equation, balance law, we isolate tank 2 and apply the balance law. Y2 prime, rate of change, amount of fertilizer, rate of change in tank 2 equals inflow 2, this time, inflow 2 minus outflow 2. Okay? Yeah. Then we set up equations. So we get a linear system. Yeah. Here you can see, yeah, for questions, application question like this, when we set up, we get a linear system. Yeah? So it's not a conversion from higher order to this one, right? We get a linear system in application. Yeah. All right. So let's continue. Inflow 1 per minute. What's the inflow 1? Yeah. Inflow, we want to calculate the amount of fertilizer that flows into the tank 1 per minute. Per minute. Yeah. How much pound number fertilizer in 1 minute flows in to tank 1? Yeah. Let's use 1 minute. Okay? 1 minute. 1 minute, you get yeah, let's assume uniform mixture, okay? Uniform mixture. 2 gallons of uniform mixture from tank 2 flows in tank 1. Yeah. Tank 2 has volume 100 gallons volume, right? 100 gallon volume. And you take 2 gallons from that 100 gallon. Okay. All right. So the amount of fertilizer, 2 over 100, right? Yeah. Because you only take 2 gallons from 100 gallons. So the amount of fertilizer you take, 2 over 100 times Y2. Okay? Yeah. So that understanding. Yeah. All right. Similarly, outflow 1, so you assume uniform mixture in tank 1, but you only take 2 gallon from 100 gallon uniform mixture, yeah, from tank 1, and it flows out of the tank 1, so you minus outflow 1, that is 2 over 100 times Y1. Okay? So that's the first equation. Second, similar, right? Yeah. Inflow 2, here, inflow 2, yeah. 2 over 100 from tank 1, so Y1. Okay? Outflow 2, yeah. So 2 over 100 proportion times Y2 amount fertilizer flows out. Okay? Yeah. So direct interpretation from the balance law. So you write these 2 equations. Yeah. Linear system. 2 equations. Yeah. Next, let's try to solve it. Okay? Yeah. Here, I only have 2 minutes. Let me just do some, general idea. Solve it. Because it's simple. Yeah, this equation is so simple. Yeah. First, you add up these 2. You can see cancellation directly, right? Y2, negative Y2 cancel out. Y1, negative Y1 cancel out. So if you, here we do all the way just, we do not use the, our new knowledge from linear algebra. We just use our all the way, okay? All the way, Y1 prime plus Y2 prime equals 0. Then the sum Y1 plus Y2 should be a constant, C1. Yeah. Derivative of a function is 0, so that function should be constant. Yeah, so we get that. Constant, so Y2 equals C1 minus Y1. Okay? Yeah. Then let's plug into the first equation. Y1 prime equals 0.02 C1 minus 0.04 Y1. Okay? This is a separable first order ODE, so we can find a solution easily. Y1 equals this one, and we need a C2, another constant. Okay? C1, C2 constant. Okay? Yeah. And we can write Y2, yeah, because from this one we can write Y2 expression. Yeah. Y1, Y2, then we use initial condition, plug in to get a C1, C2 numbers. Okay? Yeah. So C1 equals 150, C2 equals 75. Yeah. So we get a solution function here. I didn't complete. So to complete it, you just write a solution function. Then, amount of fertilizer in tank 1 is 1/2 of amount of fertilizer in tank 2. Total 150 pounds, right? So in tank 1, 1/3, 50 pounds. Tank 2, 2/3, 100 pounds. Okay? So amount of fertilizer in tank 1. But you have Y1 solution in tank 1 equals 50. So you solve that equation for T. Okay? Yeah. Because later you get this, for some T, this amount should be 50 pounds. Okay? Then you solve for T. So you get the time, that time. Okay? Yeah, just complete it. Yeah. The detail also you can find in textbook. Yeah. So, but the way textbook use the characteristic function, so it's different from this one. Here I use the old way. The new way I will talk about next time. Okay, characteristic function, the new way. Yeah. So we will do next time. Yeah. All right, that's it.